It's my pleasure to introduce Geoff Hinton, who really doesn't need any introduction.
Great, thank you. So what I'm going to talk about is, I've got a lot to say, is I'm going to give about a 10-minute or 15-minute overview of how you learn multi-layer models with restricted Boltzmann machines, and show you a recent speech recognition example where they do very well. Then I'm going to talk about how to make a better module, so the basic learning module can be improved a lot. And I'm going to show you some examples of learning how images transform over time, some examples of modeling human motion, and finally some examples of modeling the covariance matrix of an image. I've given this talk many times in the last few weeks, and some of you may have been to it, and I wouldn't be at all annoyed if you walk out right now. So a restricted Boltzmann machine has some observable variables and some latent variables, and the connectivity is highly restricted, so that in particular the latent variables don't communicate directly with each other. It's an undirected model. These variables are all binary to begin with. They're all going to be binary stochastic variables. And because there's no connections here, if I give you the states of the visibles, give you a vector there of ones and zeros, each hidden unit is independent of the other hidden units in the posterior. And the probability that the hidden unit is on is just the states of these guys times the weights on the connections put through the logistic function. So if you'd already learned weights here, you could see the kinds of things the model believed in by starting with some random state there, activating the hidden units by picking ones or zeros from this probability, then activate the visible units by picking ones or zeros with this probability, and go backwards and forwards many times until you've forgotten where you started, and that will show you the kind of things it believed in. And the aim of learning is to adjust these weights so it believes in kinds of things that look like the data. Then you'll have a good generative model of the data. And the restrictions on the connectivity here to allow the posterior to be computed very fast and exactly given the visible units. That system of visible and hidden units is governed by a Hopfield energy, where I've left out all the bias terms. The energy of a visible and hidden vector is minus the product over any visible and hidden unit of the weight between them, and if it's a big positive weight, that's low energy, which makes it happy. And the derivatives of this energy look like that with respect to a weight. So in learning, this product is going to show up or not, because the learning algorithm is going to consist of trying to make the restricted Boltzmann machine happy with data and unhappy with whatever it already believes in. Of course, if it already believes in data, they'll cancel out. So the probability, the joint probability of a visible and hidden vector is e to the minus the energy. So this is how energy is determining probabilities. Normalized by this thing to make these add up to a probability distribution. This is summed over all possible visible and hidden vectors, and so you can't actually compute it for large nets. If you want to know the probability associated with a visible vector, you sum over all possible hidden vectors that might go with it, and you get this. So if you want to increase the probability of an observed visible vector, what you should do is you should lower the energy of pairs of this visible vector with any hidden vector that would like to go with it, and you should raise the energy of all other pairs, particularly pairs that occur a lot, that is, ones that already have low energy. To do that, you can run a Markov chain where you start at time 0 with data. Given the states of the visible units, you stochastically activate the hidden units. So these will be ones or zeros, and they'll all be conditionally independent given the visible units. Then you reconstruct using exactly the same process the other way around. And you go backwards and forwards for a very long time until you've forgotten where you started and you're generating fantasies from the model. So this is the kind of stuff the model believes in. This is data. And what you should do to learn, to do maximum likelihood learning, is you should lower the energy given a data vector, lower the expected energy given a data vector. And you do that by changing the weight wij in proportion to the product of vi and hj, averaged over data vectors and averaged over the stochastic noise here. At time 0, that means with data. And then you also raise the energy of what the model already believes in. So it'll believe in data, not what it already believes in. And that's this term here. So that's the maximum likelihood learning rule. And it's nice and simple, even though this derivative depends not just on the weight on this connection, but on all the other weights. But all the other weights here show up in this correlation here. And so unlike backpropagation, where you have to explicitly go backwards through the whole net, this correlation that you're computing by this alternating Gibbs sampling is containing everything you need to know about the other weights in order to change this weight correctly. We used to run the Markov chain for a long time, and then I tried running it for less and less time. For a long time I ran it for actually 4 steps like that, because I couldn't believe any less would work. And after about a month I thought I'd try even less. And all you really need to do is this, and it'll learn just fine. This isn't maximum likelihood learning anymore, and I'm not going to try and justify it now, except by the fact that it works. What you really ought to do is, when the weights are small, go up and down and up again and take the difference of those correlations. As the weights get bigger, do a few more steps. And then if you promise that, in the end you're going to do an infinite number of steps, you don't actually have to do it. You can keep the statisticians happy by promising that you intend to do it, and then you're asymptotically correct. Then asymptotically it is maximum likelihood learning. The reason these networks are interesting, well, they actually form quite good density models of all sorts of data. But the most interesting property they have is that with these kinds of undirected nets, you can learn a layer of features, and then you have a guarantee, which is that if you now learn another layer of features on top of that, where you treat the features, that is the stochastic activation patterns in the first hidden layer when it's driven by data, treat those as data now and do it again. If you initialize the weights right and have enough units in the next layer, you can guarantee you'll improve the log probability of the original data under some composite model. In other words, adding a layer gives you a better model. And if you add another layer, you'd like to show you get a better model again. You can't quite show that, but what you can show is that every time you add a layer, you improve a variational lower bound on how good your model is. So there's this quantity that's sensible, and every time you add a layer, if you do it right, you're improving this bound. Once you know that, you're happy with the math, and then you gladly go off and add layers in ways that violate all the conditions of the math, but it works nicely anyway. Once you've learned a whole bunch of layers, you can fine-tune the system for discrimination. That is, you learn many layers of features, and they're learning to model the input data. You then add a final layer of label units, and you discriminatively train up the connections from the last layer of features to the label units, and then use backpropagation from the label units all the way through the network to fine-tune everything, and that works much better than standard backpropagation. People in Yoshio Benjo's lab, using Sami Benjo's computers at Google, have shown that you get to a different place in weight space than if you just use standard backpropagation. The minima you find this way just don't overlap at all with the minima you find if you just start with small weights and do backprop. And those minima generalize much better. And the real trick here is you're not using label information to design features. Features are being designed to model data. The label information is used to ever so slightly fine-tune the features so as to move the decision boundaries around a bit. So in particular, this approach can benefit from lots and lots of unlabeled data, because you can learn many layers of features without ever touching the label. And then if you have a few labels, you can then fine-tune to get discrimination right. But you can have only a few labels and still learn lots of features.
Are the minima better than just minimizing training loss on using backprop?
That's exactly what those experiments were in Benjo's lab. He takes small random initial weights and does backprop, versus take the weights you've pre-trained here and do backprop. And he shows that basically the distributions hardly overlap. The pre-trained nets give you much better discrimination, and what's more, the weights in a very different part of the space.
And Jeff, suppose you did back propagation first in a kind of encoder problem, which is what the...
Well, in a sense, this is a generalization of doing an autoencoder, right?
Right, and then...
Right, so Yoshio Benjo has tried things using autoencoders. They don't work quite as well as this, but they work pretty well too. So the justification for this is my favorite picture. It's got a technical concept from Donald Rumsfeld here. where if you believe that images and labels arise by stuff giving rise to images and images giving rise to labels, then it's sensible to try and learn the mapping from images to labels. For example, if a label tells you the parity of the pixels, that would be true. The labels would be independent of the stuff given the image. But you actually believe this, that stuff gives rise to images. If you don't believe this, you've probably got brain damage. You believe stuff gives rise to images, or you're in machine learning. And stuff gives rise to labels. Well, no, we had a reviewer for a paper recently, not me, but a student of mine, so I feel justified in saying this, who said, so you've shown you can build a much better density model than other methods. Why is this interesting? You haven't shown that it's better for discrimination. Okay, so you believe that stuff gave rise to images, and the same stuff is what's determining the label, like it's a cow. And if I just tell you it's a cow, you don't know the colour or position or orientation or size or whether it's alive or dead or where it is or anything like that. Whereas if I show you an image, you know all those things, because this is a very high bandwidth pathway that you can actually invert. And so the right way to associate labels with images is to first invert this pathway so you get the stuff, and then do discriminative learning on this, and then do a little bit more discriminative learning here to maybe slightly change how you represent stuff so that you're good at discrimination. But I'd regard that as a sort of minor after effect. Now, one more thing I need to do before we get on to new results is the units I was using as visible units there were binary stochastic units, and we want to apply it to data that's real valued. And if the real values are things like ink, which is sort of binary stuff, you can get away with binary units and you treat the ink intensity as a probability, but it won't work for real images. So for real images, we change the energy function just a little bit. This is the term we had before, which is visible times hidden times weight, but we're scaling the activity of the visible units by their standard deviation. And for everything I'm going to talk about today, we just set that equal to 1, which is a silly value, but it works fine. We can now learn that effectively. That's just the biases of the hidden units. And then for the visible units, we add this extra term, which says visible units would like to be near their mean value, this bias value. So this energy term, as a function of the activity of a visible unit, looks like this. It's a parabola, which is the negative log of a Gaussian. And so we're adding in this parabola, and then saying we've got an energy function for visible, for linear visible units with Gaussian noise and binary hidden units. And if you think about the top-down input that comes from the binary hidden units to the visible units, it's going to be the derivative of the energy with respect to VI, which is going to be the sum of the hidden units times the weights, scaled by this standard deviation. And so that derivative is going to look like this. It's going to say that as VI changes, the energy changes, and the most likely state for VI is going to be where these gradients are equal and opposite, so about here. Okay, so that's a linear visible unit. Using those, now let's do a bit of speech recognition. The speech recognition people have a very nice, rather old, but very nice database with a very well-defined phone recognition task. You're given a short window of speech and you have to predict the phone of the central frame. Actually, each phone has a 3-state HMM model, so there's a beginning, a middle, and an end of a phone, and you have to predict for the central frame which phone it is and whether it's the beginning, middle, or end. So there's 183 things you have to predict probabilities over. If you can predict those probabilities well, you then give it to a post-processor that's fairly standard. We're using a biphone model. Some people use a more powerful model. Some people at IBM very recently reported results comparable to ours. They're using a triphone model, which is a bit more powerful. So if we can predict these well, sensible distributions, the post-processing will decide where the phoneme boundaries are and will report the phone error rate, so we can see how well we're doing. And in doing that, it collapses the phones into broader classes and reports the rate for these broader classes. So George Dahl, working with Abdo Mohammed, who knows a lot about speech, just made up a net off the top of his head, pretty much. And the input is 39 Mel-Kepstrel coefficients, where there's actually 13 of them, and then the differences and the differences of the differences. And he just trained up lots of layers of lots of binary units. So this is kind of dumb, but he wanted to see whether it would work. So all of these green connections, there's 4 million there between each two layers, they're all trained unsupervised, and they're being trained to model the structure in the input. And there's quite a lot of structure in the input. And he then went down to a bottleneck, although it turns out this isn't really necessary. And so that the weights that he couldn't pre-train, the weights that he had to learn purely discriminatively, were limited in number. And so he learned these discriminatively now, and then he back-propagated through all of these to fine-tune these. They didn't change much, but he fine-tuned them all for at least a day on a fast GPU. And he gets 23.0 phone error rate. More interestingly, as he varies the number of hidden units in each layer and the number of layers, all his results are between 23 and 24. The best previous result before this very recent IBM stuff was 24.4 that we know of. When we told the Microsoft speech recognition people we got this, they didn't believe us and demanded to see our confusion matrix. So we sent our confusion matrix and they said, okay, maybe you did get that. And now they believe it. So it's quite a good result. Okay, on to the new stuff. We want a more powerful module, and the basic module that we're training can't do multiplies. It can sort of fake them because it can fake anything with enough layers, but it's not very happy doing multiplies, and multiplies occur all over the place. In particular, whenever you see a heavy-tailed distribution, an easy way to get that is take two Gaussian distributions and multiply them together pointwise, then you'll get a heavy-tailed distribution. And so they're a sort of signature that there's multiplies around. And it's been used in a lot of places in machine learning and computer vision. Here's the sort of main reason I want multiplies. Suppose I tell you a shape, the name of a shape, and I tell you its position, orientation, and size, and I want you to generate the pieces of the shape. I'd like a hierarchical model that can do that, and can do that sort of well, and can learn to do that from data. And one way I could do it is to generate the pieces very accurately, so that the relations between the pieces come out correct. An alternative way is generate the pieces very sloppily, so this is meant to represent a distribution for this side, and this is a distribution for that side. But I could also send down some information about how things should interact. And this information about how things should interact would allow me to clean things up. Okay? So when I clean things up, sometimes I'll get that square, sometimes I'll get a square a little bit bigger or in a slightly different position or slightly rotated, but it'll always be a nice clean square where the edges fit together and fit with the corners. So that's a much more powerful kind of generative model. Rather than one level saying exactly what should happen at the level below, and then what happens there being independent given what the signal that comes from above, the model above says how things should interact at the level below. In effect, you're downloading an energy function, and the level below is solving to find a good solution to that energy function. In a big hierarchical organization, you can tell people below you what they should do, or you can just give them the energy function and tell them to get on with it. And that tends to work much better. Here's an example of if you want some soldiers to stand in a rectangle, you can tell each soldier exactly where to stand, but you have to tell them very precisely if you want a nice rectangle. Or you can tell a soldier roughly where to stand, and then you can say the next soldier should be at arm's length from him. So you're specifying the interaction. And then you can get a nice neat rectangle while sending down much less information. So we want to make a module where the hidden units control the interactions between visible units, and then we want to stack that up. Now, we haven't actually stacked these guys up yet, because already when we just make that module, it does really nice things. We've been focusing on exploiting the really nice things it does. So what we do is we make a more complicated energy function, which Terry suggested a long time ago. Instead of an energy function that says a visible state times a hidden state times a weight, we're going to have a visible state times another visible state times a hidden state times a weight. And you can see that if this hidden unit is turned off, this weight doesn't exist. It's like switching that weight. Whereas if this hidden unit is on, you've got the weight Wij between Si and Sj. Because it's symmetric, any one can be viewed as switching in a connection between the other two. So some time ago, Roland Memisevich and I got this to model image transformations, where if you think about an image with random dots in and you're translating it, then if these two dots go to there, you can think of using a three-way weight that says this dot going to there is consistent with a certain translation, and what's more, this dot going to there is consistent with the same translation. So if we put big positive weights there, when we see that pair and that pair, we'll activate this guy. Or conversely, when we see this and we activate that guy, we'll get lots of input to these guys and we'll turn those guys on. Alternatively, if these dots went somewhere else, you'd activate some other transformation. And actually the transformations could have some distributed representation, that would be fine. So that worked nicely, but it only worked for small image patches because there's so many of these guys. They're third order things, and so there's kind of cubically many of them. If I have n of these, n of these, and n of these, I've got n cubed possible ones of these. So we can get around that by factoring things. Basically we're saying if you consider pixels translating in an image or transforming in an image, they don't transform in totally arbitrary ways. You don't get these pixels going to kind of, well, I can't do it with my hand because that wouldn't be arbitrary. And so that what I can't do is what they don't do. So we presumably don't need that many parameters. That's just a waste. So what we're going to do is we're going to factorize that thing by saying we're going to have a factor, and each factor has, if we have n factors, we're going to have 3n squared instead of n cubed. And our energy is now going to be the state of a visible times the state of another visible times the state of a hidden times these three weights from the two visibles to the factor and from the hidden to the factor. We can picture it like this. We take the outer product of these vectors. The outer product of those two gives us a matrix. This is just scaling that matrix. So it's a rank 1 matrix here. This scales the rank 1 matrix to get the same matrix at different scales. So this gives you a rank 1 tensor. If I add up n squared of these, I can get, I think it's n squared, I can get an arbitrary tensor. But if I add up many less than that, I can't get arbitrary ones, but I didn't want arbitrary ones, I wanted nice regular ones. So I should be able to factorize. In that model with the three-way factorized energy function, here's how inference works. Let's suppose we're trying to learn image transformations and you have a pre-image and a post-image. Here's the pre-image, here's the post-image. A factor will have a set of weights to the pre-image, so it's going to compute a linear filter on the pre-image, the pixels activities times the weights, a linear filter on the post-image, the pixel activities times the weights, and then the inference procedure works like this. Multiply those two sums together, that's where the multiply is now, and send that message, which is this product, to all of the hidden units, and on the way multiply by WHF. And if you do that, what this hidden unit will receive is the derivative of the energy contributed by this factor with respect to the state of that hidden unit. And that's what it needs to see in order to decide whether to be on or off. It's going to try and adopt whatever state lowers energy, but with a bit of noise. So that's belief propagation, because this factor, it's sending this product there, and if you want to reconstruct this image, it's going to take this times that and send it here. So it's sending to each thing a message that doesn't involve the information that it got from that thing. Yes?
In the unfactored version, if you just train that up, you always end up in a situation where the weights can then be factored in the way that you described?
No, not necessarily. One problem you'll get is training up a big one will take an awful long time because there's so many weights.
But in the image patch case,
on a small image patch, if you trained it with too many weights, you're right. You would hope that you'd end up with something that at least approximately could be factored. So you ought to be able to train it and then factor it to show that it didn't need all those weights. That would be a good control experiment, I agree. Yeah. So this is just saying what I just said in equations. This is the message that factor f sends to hidden unit h. It's the product of these two sums. If you look at the learning algorithm, how you change this weight in order to improve your model of the data is the difference of two derivatives. The derivative of the negative energy when you're showing it data, and the derivative of the negative energy when you're sampling from the model. And we're going to learn a conditional model here. That is, to begin with, we're going to learn to model this conditional on that. So that when you apply the learning algorithm, what you do is Given this and this, you activate the hidden units. And then given the hidden units and these, you reconstruct that, and then you activate the hidden units again. So that's nice and easy if you condition on these, because then you can, all these remain independent. Of course, the whole point of this kind of model was to get correlations here, but we'll come to that in a bit. So the learning rule is still nice and simple. It's just the learning rule for a weight is just the product of the message that comes from the factor times the state of the hidden unit. And the state of the hidden unit is the message that goes back from the hidden unit to the factor. And it's that difference with data and with reconstructions, or if you sample long enough with samples from the model. So here's what it learns when you show it translations of dot patterns. Here's the pre-filter, the filter to the pre-image. Here's the filter to the post-image. And here's a whole bunch of those. And that's the post-image, pre-image, post-image, pre-image, post-image. So it learns basically the Fourier basis. It learns a whole bunch of gratings of different frequencies, roughly 90 degrees out of phase with each other. Here's what it gets if you do rotations. Okay. And one more thing about it. If you train it up on patterns that are 10% dense, and then for the first time in its life you show it two patterns that are 5% dense, one going one way and one going another way, so it's never seen transparent motion before, and you want to know what it sees. Well, this whole thing was trained unsupervised, right? There was no labels anywhere. So how do you figure out what it sees? We put an extra layer on top, which was a sparse layer. By making it sparse, you make the fields fairly selective, and those units in the extra layer on top that's learned entirely unsupervised will be tuned to particular directions of motion. And so now when you give it an input pattern, you take the preferred directions of those cells, average them, and that's what it sees. You claim that's what it sees, perceives. If you give it two dot patterns moving within about 30 degrees, you get one big mode there. It's seeing one direction of motion at the average. If you move them beyond about 30 degrees, you start getting two modes, and what's more, they're slightly repelled. That's just what happens with people. So the claim is this might have something to do with how people perceive motion. It's a rather weak claim, that, but at least it does the right thing, and it was never trained on transparent motion, and it never saw a label in its life. Okay, we're now going to apply the same ideas to learning time series models for fairly high-dimensional time series. Not as high-dimensional as video. Most people use directed models. It's hard to fit those to data if they have nonlinear representations that are distributed. The easy ones to fit are HMMs which have localist representations. That is, when they run as generators, each frame is generated by just one node. Or linear dynamical systems that have distributed representations but are linear. We're going to try and get an approximate learning algorithm for something that's much more powerful in the following way. This is a restricted Boltzmann machine. One of the just two-way ones, not a three-way one yet, but we'll get there. Where we have visible units, hidden units, and we condition on some previous frames. These are all going to be linear units, so this conditioning is an autoregressive model. It's just saying these linear units are this previous state times a big matrix, plus Gaussian noise. We're also going to have binary hidden units that are conditioned on the previous frames. And the idea is that the nice smooth motion is going to be modeled by the autoregressive model, but when sudden changes happen, these binary hidden units can override by providing top-down input. So the learning algorithm is simply, given these three frames, you activate the hidden units, which are all independent still. Then given the states of the hidden units, you reconstruct the visible frame, the current one, using the top-down input from there and the autoregressive connections from there. Then you again activate the hidden units, and now you look at the difference in the correlations here when you're looking at data or when you're looking at reconstructions. That'll learn these weights. The difference in the activities for data and for reconstructions here can be backpropagated through these connections to learn the weights on these connections. And the difference of these activities is backpropagated here to learn the weights on these connections. So it's easy to learn. After it's been learned, you can sample from it. You can see what the model believes in by taking some conditioning frames, They provide input to these units, and they provide input to these units. So you can add up all those inputs, and in effect, you've got a Boltzmann machine here whose biases have been set by the previous frames, and you just go backwards and forwards for a long time. You don't really need to go backwards and forwards for that long, because given the strong biases coming from the previous frames, there is some noise here, but it can't do sort of crazy things. So going backwards and forwards half a dozen times is sufficient to sample a reasonable state there. That's your next frame, and you carry on.
It looks like there's no time-varying connections between the hidden units, is that right? On that.
In this model, there's no connections between the hidden units. This is a model that just transduces visible sequences into hidden sequences. Yep. It's not a state model, state space model. Okay. If you want a state space model, you learn that, so you've transduced visible units into hidden units. You now apply exactly the same learning algorithm here. And if you were to do it right, you could improve, you're improving things. This isn't quite right what I've done, but it'll work. And so the idea is you don't put in connections between units, lateral connections, until they become visible, and then life becomes very easy. And because we've got this greedy learning algorithm, you're never having to deal with inferring hidden states that are complicated. After you've learned all this, the inference procedure for these guys completely ignores these units, these connections. These connections are used in the generative model, so they're used for reconstructions, but the inference procedure isn't changed by modeling this. So you've still got simple inference. To generate from this sequence, you'd go back, given these frames, you go backwards and forwards here, and you'd think about generating at this higher level. Once you've generated a sequence at that higher level, then you get top-down input here, autoregressive input here, and you can generate that. But basically you have to go backwards and forwards here, but just down once here.
So the number of hidden layers varies as time, right? So you could have, I mean, as t increases, you have potentially an extremely long chain of connections that you may want to pre-train, right? So how does pre-training...
This is a limited window. This isn't the whole temporal history. So we're really learning a model of a window on a sequence.
I see. The windows are overlapping, though, right?
But it's true that this guy is connected to these guys, and this guy is connected back here. So if you use the same temporal resolution at every level, the amount of history you see goes up linearly with levels. If you, for example, halve the temporal resolution at each level, but kept the same number of frames, you can make it go up exponentially. But you don't have a huge amount of work still. I mean, you can infer these from these, and then you can infer these from these. The inference all breaks down like that. So you can get efficient inference even if you have a lot of layers and a very big window because you're using coarser scales higher up. We're not going to use that model, although it works well. We're going to take a sort of three-way version, and we're going to apply it to motion capture data where you put markers on the joints, you have infrared cameras that say where they are in space, you then figure out the joint angles, and each frame of data is now a bunch of joint angles plus the translations and rotations of the base of the spine. And what we're going to do is, we have 6 previous frames here, so here's our autoregressive model. Here's our restricted Boltzmann machine, but it's a 3-way one now. But instead of conditioning it on this and this, what we're going to do is we're going to say, we'll tell it the style. So this is labeled training data. It's trying to model the sequences given the style. So it's trying to do a conditional model of the input given the label, exactly backwards from normal machine learning. And these are our 3-way factors, and there's a whole lot of them. And so it'll get a derivative here which it can backpropagate to learn all these weights and these weights. And what's happening is the style gets turned into some real value features which allow it to generalize a bit between styles and to blend styles. And the real value features then act to modulate the autoregressive model. So what's happening here is, this is much more powerful than, say, a mixture of autoregressive models, where you have to pick one of these models. These variables can blend the models together. So, for example, these variables might decide that what you're doing with the arms is just right, but I want you to do something funny with the left leg, but keeping the arms the same. Or maybe modulating the right arm a bit when you modulate the left leg. So you've got compositionality here still. Okay, and we train this up by you give it the style, given these frames, you can activate those, and given these units, these are all conditionally independent still. So we activate those, then we reconstruct those, then we activate those again, and then we get derivatives we can backpropagate here, here, and here, and we also get the derivatives we can train those. So here's what it does if you generate from the model. If Vista will allow me. Okay. This is a normal walk. So this is a student at CMU. I think he's a student. And this is actually now running the generative model to show that it's really captured what's going on. He's deciding which way to turn. And as you'll see later, he can also do things like stop and start again, which autoaggressive models can't do. You can make him walk in like a gangly teenager. So you see the style is having a big effect. Now, one way to think about this character is I've got a pin stuck in the base of his spine, and I'm moving him about with this pin and making him sort of go up and down and rotating him with this pin, and he's waving his legs in space. And if he waves his legs in space just right for the translations I'm doing with this pin, then his feet will appear to be stuck to the ground. So if his feet appear stuck to the ground, that means he's getting everything dead right. Insofar as his feet are skating, he's not getting all the variables exactly consistent with each other. But it gives you a very visually obvious model of how accurate it is. Now, he doesn't have a physics model, so when he stumbles like that, there had to be something in the training data like that. You see, he stopped there and started again. Very hard to do with an autoaggressive model. He is graceful. And hopefully you recognize this character. It's C3PO. I don't think he was told to do C3PO. It's just the only graceful thing he'd ever seen. I sort of... It's very bad of me. This student is a very good actor and did these walks brilliantly. And I owe a lot to him, so I shouldn't make fun of him. You can get him to walk softly like a cat. And so if you look at the foot skate, you can gauge how accurately things are going. And the fact that he could stop and then start again and walk at a different speed is all things that make... you need a non-linear model for that. We could get him to do a sexy walk, and then halfway through we could switch the label to normal. And because it's all one model, he should be able to transition even though he's never seen a transition in his life. Now, presumably the transition isn't getting all the momentums exactly right, because it doesn't know anything about physics. But it's doing a pretty good job. At least it knows what phase of one model corresponds to what phase of the other model, because it's all one model. It's back to sexy again. Okay, so that's an example of modeling high-dimensional data, and obviously we'd like to apply that kind of model to video, but we haven't. We've done it for simple examples, but not impressive ones yet.
Excuse me, Chris, how do you get the training data for the different styles?
The guy walks in those different styles.
Oh,
He's told to walk in those styles.
Oh, okay.
So you know for the data what the style was meant to be.
And
you condition on it as you're training.
you label different styles?
Yeah, they're labeled.
Okay.
So we're training a conditional model of this motion given this style.
Right.
You expect to do it the other way, right? You expect to be learning a model of the style given the motion. Mm-hmm. And we can do that too. We can actually learn mixture models of these styles. And for tracking, we just got a paper accepted for tracking at CVPR, where you can use this model for tracking. So you have a particle filter, and what they normally do in particle filters for tracking is say, okay, I've got these particles that are still alive, and I'll add a little bit of noise to the configuration of each particle, and then see how well they fit the data. And instead of adding noise, a particle has a whole history. So you could say, well, where would this guy walk next? What would be a reasonable next frame given what he's done so far? And this works much better than just adding noise to a particle, obviously. And for doing that, we actually did learn a mixture model of the motion. So you take sort of one motion and learn a mixture model. And so you break up motions into a bunch of sort of stylelets. And that works nicely.
How much memory do these systems have for learning? How many frames do you go back?
So the walking guy was 6 frames there. So that's kind of typical. When I draw it, I only draw 2 because I'm lazy. But yeah. With the visual motion, the moving dots, it was just 1 frame of history. Okay. So the easy case to do reconstruction in is where you condition on this, and this is what you're trying to model, this conditional on that. But for images, so I can get the same picture, what we're going to do is take 2 copies of the same image. So copy 1 and copy 2, and they have to be identical. So this is the case where the hidden units are controlling correlations between pixels now. And in fact, if I turn on that hidden unit, then, and if this factor didn't have anything else feeding into it, then that hidden unit would send a message of WHF times WIF times that state times this weight to there. So the effective weight between I and J would be the product of those 3 weights, okay, if I turn on this hidden unit. Now, because these have to be the same, the reconstruction is much more difficult now. I can't just reconstruct that holding this fixed. We'll come to that in a minute. I'm going to make these weights be the same as those weights because they're the same image. So this now degenerates into something where you take this linear filter and you square it and you send the output to the hidden units. That's a very standard model of images. That's the oriented energy model of images that Adelson and Bergen introduced a long time ago. And neuroscientists have also sort of suggested this is a model of simple cells and complex cells. So these factors look a bit like simple cells, and these hidden units look a bit like complex cells. But we got this structure. We didn't arrive at this structure by sort of trying to model the oriented energy model. We arrived at it by taking a 3-way energy function and saying what happens if you factorize it. And one advantage of that is we end up with a nice simple learning algorithm for all these weights. We end up with a way to reconstruct, not just a way to perceive. And so, for example, we can show you samples from this model. And the advantage, another way of saying the advantage of modeling covariances between pixels, modeling weights between pixels, is that if I ask you what a vertical edge is, some people would say it's something that's light one side and dark the other side, or maybe dark light the other side and dark the first side, or maybe sort of light up here and dark there, but then dark here and light there, or maybe it's actually there's motion on this side and no motion on that side, or different motion on that side, or maybe it's a disparity edge, or actually there might be a texture here and a different texture there. And it sounds like a vertical edge is a disjunction of a huge number of sort of things. They all have one thing in common, which is a vertical edge says you shouldn't interpolate horizontally. Whatever it is you're interpolating, don't do it horizontally. You can do it vertically along the edge, but you mustn't do it horizontally. This, if it's a vertical occluding edge, is the cleanest case. So what we're going to do is try and have these hidden units that model how you interpolate. That is, they model weights between pixels. And what they're going to do is they're going to turn off the interpolation. So actually, when the hidden unit's active, it's going to be saying, put in this interpolation. If you find a vertical edge, what we want to do is turn off that interpolation. So we're going to have some kind of reverse logic for these hidden units. In a real brain, you'd have the logic the other way around, if you had anything like this at all. Because the hidden units create dependencies between the pixels, we can't just reconstruct simply. What we could do is say, given the states of the hidden units, they define a whole bunch of weights. That's the inverse of a covariance matrix. We could invert the matrix, and then we could sample from that Gaussian, a full covariance Gaussian. But that would be expensive. So instead we use a method called hybrid Monte Carlo, which essentially starts at the data and moves a little bit in the direction of the energy function defined by all these weights, and does it in an efficient way so that it can move further than you would if you did it in a dumb way. And that, it moves a little bit to get to the reconstruction. Then you activate the hidden units again given the reconstruction, and after that everything's the same. It's the same learning algorithm. So that's what I just said. So now what we're going to have is a system that has these hidden units that have the three-way factors, but it also has ordinary hidden units. You see, ordinary hidden units are good at modeling the mean values of pixels, and these three-way guys are good at modeling the correlations between pixels, and we want both. So we're going to have two different sets of hidden units. So here's a little demo of what happens if you learn on 16 by 16 grey level patches. There's an image patch. Here's the stochastic reconstruction from the states of the hidden units and the states of the hidden units that represent covariances, and the states of the hidden units that represent the means, and it's pretty good. This is the average of all the stochastic reconstructions, which is almost perfect. What we're going to do now is we're going to lie to it. We're going to say, let's take our covariance matrix that we extracted from this image. That is, using this image, we activated the hidden units that have these three-way factors, and they're modeling the covariance of pixels. They're modeling the fact that these are the same, and these are the same, and these are different from those. And let's take all the information that's modeling what intensities they actually are and throw it away, and put in fake information. So we tell it, look, I'm telling you all these pixels, my information in the means is that all of these are sort of average grey, except for these which are dark. Now try and reconcile the information about the means with the information you believe about the covariances, and it produces that. In other words, it blurs this out, but it blurs it out this way. It doesn't blur it across the edge. And because this is dark, it makes that a bit lighter. If you put in just 4 blobs of paint like this, plus the covariance, it'll blur them out and produce something quite like the original image. And this is kind of the watercolour model of images. The thing that says you sort of know where boundaries are, and you know roughly the colours of regions, and that's really all you know. You don't need to know for every pixel exactly what it is, because your visual system can sort of figure that out. And so here we're showing it, figuring it out, that this is the sort of best bet given blobs of paint like that, but the covariance matrix that came from there. If you look at the receptive fields of the hidden units representing means, they're sort of blurry, cloudy things. There's no sharp edges. And basically, if you take a subset of these, take sort of 50 of these guys, and you can model any sort of pattern of intensity over the image you like, as long as it's smooth. You won't get any sharp edges. So it's quite good at modeling the colours of regions by picking the right subset here. If you look at the hidden units that represent the covariances, so we're going to take the factors that feed into these covariance units. They look like that. I'll tell you in a minute why it's a topographic map. But one interesting thing is that all the high-frequency ones are almost pure black and white. That is, at the early stages of learning, these were coloured, because what I'm showing you here is the receptive field to the RGB channels. Sort of out of perversity, we didn't change it to a more natural basis for colour. We showed we could just do it with the RGB. So you see this looks a bit like a monkey's cortex because the orientation changes smoothly. This looks even more like a monkey's cortex because you get a big colour blob of low frequency cells which are either red, green or yellow, blue. And this all just popped out of the learning and the structure of natural images. Monkey's DNA doesn't need to know you should have colour blobs. It might well know you should have colour blobs, but it doesn't have to. You could get colour blobs anyway. One reason for this separation, I think, is because in real images, a large fraction of the edges have zero colour contrast, and that's because they're things like my nose against my cheek. It's the same material, and the illumination isn't changing its colour in different directions, just its intensity. So you get a lot of edges with no colour contrast, so these guys make sense. And then if there is a colour contrast, you can activate some of these too. I think that's why it does it.
So these covariance guys are the ones that correspond to the complex cells? Or?
No, all of these are complex cells.
Right. And why do they then look like simple?
Sorry. Let me go back to the picture. What I'm showing you is these weights here. Okay? So the weights into the simple cells that feed to the complex cells. But in the circuit that has complex cells. We got another circuit for the means that just has these guys connected directly.
And the other ones would have kind of phase displaced.
Yes, so if you now take one of these guys and look at the different factors that it likes, they will be phase displaced factors so that it behaves like a complex cell. Yeah. The reason it's a topographic map is this is a trick due to Arpo Hyvarinen. You take global connectivity there, so to learn local factors, and then you have local connectivity between the factors and the hidden units. And it's basically paying a penalty when it says that smoothness is broken down. And that penalty, you only pay once by turning off a hidden unit that's representing smoothness. And so if you have two units that go on together here, you'd rather they connect to the same hidden unit, so you only pay the penalty once. That's a very quick explanation. But that causes nice topographic maps. But notice the local connectivity isn't in the factors. They learn to be local. But the ones with similar receptor fields learn to be near one another because of the local connectivity here between factors and hidden units. So here are samples from the Berkeley color patch database. And here are things generated from a model learned by Marco Aurelio Ranzato. And they're not quite right. There's too many smooth ones. And there's a sort of psychological factor, which is that the range of colours here is quite like the range of colours there. So that sort of looks like this to you. As you look at it more and more, you'll see this isn't perfect. But I think this is a much better model than anybody else has got, with the possible exception of Mike Lewicki, though I don't know if he's done it with colour. This is a much better model of what patches of images look like. They're mostly smooth, but they have sudden outcrops of structure, and they can even have sort of several bits of structure at the same time in. They can have sort of texture things in. So the claim is just these look quite like those. Whereas if you generate from most generative models of image patches, what you get is things that look like that. So if you match the second order statistics, you get stuff that is sort of clouds that have the right spectral properties, but don't have this property of being very smooth and then a sudden breakdown of smoothness. And the last thing, here is, almost the last thing, here is a difficult shape recognition task. So there's 80 million tiny images collected at MIT. We hand-labeled 60,000 of them, 50,000 for training and 10,000 for test. And you have to do a 10-way discrimination here. And we deliberately chose similar ones like car and truck, wherever truck is, I can't, truck, yes, and horse and deer, as well as some fairly different ones. It is clearly using some background information because among animals and man-made things it confuses bird and plane the most, which strongly suggests it's using background information, although they both have wings. But if you look at birds here, you know, there's a chicken, there's an ostrich about to peck you. Here's a more sort of typical bird. This is a sort of real recognition task, and it's difficult. Marco Aurelio trained on about 2 million unlabeled images to get the hidden units for the covariance guys plus the hidden units for the means. And he did it with a model of 8x8 patches and then replicated those 8x8 patches across the image, so he had 49 of them. That was partly because at that time we couldn't train 32x32 patches, it was too slow. He can do that now. That gives a total of 11,000 hidden units, and then you can try doing discrimination. And to keep life simple, he just does logistic regression on the hidden representation and doesn't try and fine-tune everything to get better discrimination. And so what you get is if you take pixels and do logistic regression, you get 36% correct. If you do gist features that Toralba and people designed at MIT for capturing the gist of an image, these are fairly low dimensional, you get 54% correct. So given that there's only 384, they do quite well. If you take a Gaussian binary RBM, you get 60% correct. If you take this down to 384, you do slightly better than gist features, but only slightly. If you take the RBM model with means and covariances, and a lot of these factors, you get 69%. And if you then add an extra layer of 8,000 hidden units, so notice that's 100 million connections right there. They're going to be trained unsupervised. You get 72%, which satisfyingly is twice as good as that. Now he's just redone all the experiments for the paper, and this has gone down to 71%, I think. It just varies from run to run, but it's pretty good. That's the best result reported so far on this database, but then not many results have been reported on it. And one final thing, we took this model designed for vision and said, what if we applied that to the speech problem? So instead of taking Mel-Kepstrel coefficients, which are designed for making things independent, so a hidden Markov model with a diagonal covariance matrix can deal with them, we just take log filter bank coefficients, and we treat it as a vision problem. The very first time George ran it, he decided to use that many covariance units, that many mean units, and then have 4 more layers like that, and he got 22.7% error, which was a record for us. And at the time, I think it was the record. There's people at IBM now getting very similar results to this. He then, within a few days, he tried a slightly bigger input and more hidden layers, and he got 21.6. And that is the record at present, as far as I know. The people at IBM just reported 21.7%, but with a more complicated post-processing model, which is worth about 0.5%. So the people at IBM with our post-processing model would be at about 22%. But there are other people who are getting comparable. But this is considerably better than things used to be. So here's what recurrent backprop got on Timit. Here's the 2009 record. And that was a method that didn't use neural nets, so I'll call that artificial. We're neurally inspired, and we're almost a third of the way from the artificial to the real. And so if we have 2 more ideas, we'll get there. Okay.
Reverse Moore's law.
Okay, I'm done. Yeah.
Have you tried generating from the auditory model?
Not yet. And it would be a very interesting thing to do. The problem is George has to finish a master's thesis by April, so he had to stop everything when he got this result. And I was saying, try this, try that, try that, try that. And he quite wisely decided he'd actually write it up. So, but starting in the middle of April, we'll try all these things. Yeah.
In this object recognition task, could you somehow use your hierarchical model to trace back actually what in the image caused a certain decision, what object it is?
I'm tempted to show you something that sort of half answers your question. Oops, I got rid of the talk. If I can find it. Oh, Vista's rearranged my desktop, that's kind of it. Okay, this is a model that's not the 3-way connections, just normal RBM stacked up, and three layers of them, and it's trained with label units at the top. And then after it was trained, I would make an image. These are images, and I made them by taking 1/3 of the pixels of a 3 and 2/3 of the pixels of a 4, chosen at random, and adding them together. So that's noise of the very worst kind, because during training it didn't see any noisy images except what's in the data, which isn't very noisy. Because the noise is from a structured object of a kind it knows about. So let's look at this one, because I like that one. You add that to that and you get this. And then what you do is you go from the input to the hidden units and you reconstruct. And that's the means of the reconstruction. So it's sort of seeing that in terms of strokes. But then what you do is this. So this is held fixed at that noisy image. Oh yes. This is held fixed at that noisy image. We've trained up this RBM, and now we can think of it as a generative model this way and a recognition procedure that way. We've got labels here. So the model looks like this. I'll do it like that. There's 2,000 of those. There's 500 there, and there's 500 there. It's a very nice model of digits and can generate digits nicely. You show it one of those inputs, and what you do is, on the first pass, actually, I'd better do this properly. On the first pass, you do 1 times those weights and 0 times those weights, and 1 times those and 0 times those, and 1 times those and 0 times those. So that's a pure bottom-up pass. Okay? Then on the next pass, what you do is I think I did 0.8 of those and 0.2 of that. Actually, no, sorry, that's always 1. And this one's always going to be 1. Yeah, so, sorry, that one's always 1, that stays at 1, and that stays at 1. This started off at 0. Now on the next pass, you do 0.8 of this and 0.2 of that, and 0.8 of this and 0.2 of that. So what's happening is you do a pure bottom-up pass to initialize everything based on the data, and then you start adding in top-down information. Now, if I did a pure bottom-up pass and I added this to the bottom-up information, I'd be double counting, because this depends on the image, and so I'd be taking data from the image, using it to decide the probability of a feature, and then using it again to make the feature even more probable. That would be wrong. But I can do model averaging. It's okay if I take 0.8 of the bottom-up model, because that's one RBM that knows how to model this given that. This is another RBM that knows how to model this given that. And I can average what those two models want to say. So 0.8 of this and 0.2 of that. And then on the next iteration I do 0.6, 0.6, 0.4, 0.4, and so on. And then on this iteration I think I'm doing now the other way around. That's 0.8 top down and 0.2 bottom up. And what you get is that it does a nice cleanup of the image. It's far from perfect, and this was just done in a hurry like 3 years ago for a grant proposal. And the grant proposal said that that's what we were going to do, and we actually haven't done it. That is, we haven't taken this any further. But it clearly works. That is, what we're doing is figure ground segmentation by using top-down information to suppress noise here, which is not exactly what you wanted, but it's close. And this is the answer to people who say, but you got rid of explaining away from your model, so how do you do segmentation? And the argument is, well, we're only ever going to try and do segmentation of a figure from ground. We're never going to try and do more than that at the same time. And what we're going to do is separate figure from ground in just the same way as we deal with invariances, which is a little bit at a time, but also we're going to then feed in the top-down information to gradually separate them, rather than try and do it bottom-up early on. We're going to do it top-down with lots of context. Sorry, that was a long answer.
Are you still, are you always doing multicolor sampling, or are you doing any of your fancy techniques? Do you always do?
Okay. Now, I've been away for a month. Basically, all of the stuff I reported is CD1, but with hybrid Monte Carlo when you're doing the covariance stuff. That is, to do the reconstruction, you start at the data and take lots of little steps like a particle would if it had random momentum and was moving under the influence of the energy function. And you do that for like 20 steps. So that's sort of one step of hybrid Monte Carlo. And then you stop, and that's your reconstruction, and then you activate the hidden units again. So that's CD1, but with hybrid Monte Carlo for the reconstructions. Now, I've tried these kinds of models with what's called persistent CD, and they work with that. And Chris Williams and Nicholas Heath and I have a paper doing textures using hybrid Monte Carlo with PCD, and it works better than just with standard CD. But we haven't used that here yet, and it's one of the many things we can use to improve this by doing fancier learning algorithms.
You never use score matching?
No, we never use score matching. That's a rival camp. Score matching is a very sensible thing to use, and around here they have things that work even better. And we haven't tried those yet either. Okay, thanks.